We're going to see how to extract a right triangle from some other shapes that we have in geometry and therefore trigonometry. And it's important to not just draw out these special right triangles that I talked about in the lecture and just give you a bunch of information about them. You need to understand where they come from. And that helps you understand why the properties are what they are. So more than just a memorization thing, it's a conceptual idea, and you need to have those concepts down in your mind. Let's start with a square. And we know that squares have all the sides are the same length, so they can be any length. So I'm going to call them T. And we know that squares have angles that are all the same measure, and those measures are 90 degrees. So all the sides are congruent. Whatever length they are, we'll call it T, can be anything, but all four sides are congruent to each other. They're all the same length, T. All the four angles are congruent to each other, and they are all right angles, all 90 degrees. What we do next is we draw a diagonal across this square. And what we get when we draw that diagonal is we see there's a right triangle here in the square. So from it, we extract a right triangle. And you're going to hear me say that a lot in this class. One of the most important skills you can have in working problems in trigonometry is seeing where you can extract a right triangle. We'll run into that a lot, especially when we get to word problems. So let's start by introducing it now. We had a square, we drew a diagonal, and from it we extracted a right triangle. And the right triangle, the two legs are size T, or length T. And we know that there is that right angle there. And so what we have here is our first special triangle is called an isosceles right triangle. Now we saw earlier that right triangles have the interior angles that are not the right angle, we'll call these A and B, that they add up to 90 degrees. So angle A plus angle B, when we add those measures together, we get 90 degrees. But we also saw earlier that isosceles triangles have base angles, any isosceles, not just a right isosceles triangle, but any isosceles triangle, if this side and that side are congruent, then this third side is called the base angle, and this, is called the base, and these two angles are called the base angles, and they are congruent or the same measure to each other. So if we know that the two interior angles of our right triangle add up to 90 degrees, and it's an isosceles right triangle, that tells us that angle A, the measure of it, is equal to the measure of angle B. And since they add up to 90 degrees, that tells us that twice the measure of angle A, because if we add A and B together and they're equal, then that's the same as adding A together, A to itself twice. That tells us that twice the angle, the measure of angle A is 90 degrees, which tells us that angle A has a measure of 45 degrees, and that has to be the same as angle B. So this isosceles right triangle has two sides that are congruent, And the two angles that are not 90 degrees are equal to each other, and they both measure 45 degrees. We also get to think about the hypotenuse, which we can label here as C. And we know, because it's a right triangle, we know from the Pythagorean theorem that the square of one leg plus the square of the other leg is equal to the square of the hypotenuse. And that means that twice the square of one leg is equal to the square of the hypotenuse. And that means if I take the square root of both sides, that the length of one of the legs times the square root of 2 is going to be the length of the hypotenuse. So I'm going to pause the recording for a moment, clean my board, and summarize what I have here. Our isosceles right triangle has two legs that are congruent, the same length. We saw that the hypotenuse has the length of the one of the legs times the square root of 2. And we saw that when you look at the right angle, the other two angles are congruent, and they both measure out to be 45 degrees. This is one of the special right triangles that you need to know. Please understand that what that T represents is the length of a leg, and that value can be anything. What's important to recognize is that having an isosceles right triangle means that these sides are equal to each other, and the right angle, the hypotenuse, that is the opposite of the right angle, is going to be the length of the side times the square root of 2. Sometimes we simplify this picture down, but you need to understand how both work. T can be any number. So if we made it 1, then we know that the other leg has to be of length 1. And we know that the hypotenuse has to be the length of the square root of 2. The angles inside are still 45, 45, 90, which is another name that we use for this special right triangle. It is often called a 45, 45, 90 triangle. Notice how I wrote in the degree symbols along with saying 45, 45, 90. I don't always have to say the degree when I'm using this name for this particular triangle, but when you're writing it down, always practice to put in the degree symbols, because otherwise you're not talking about degrees, you're talking about another unit of measurement. Make it a habit so you don't lose points on a test. This is our right isosceles triangle, also known as a 45, 45, 90 triangle. It's one of the two special right triangles. You need to know how we get to it. You need to know the relationships between the sides. You need to know the measures of the angles. We're going to use them so much this semester that it should go on that special sheet of things that you need to memorize. I even include for you a special sheet that has a place for you to draw all the different angles that we're going to learn, and it has the two special triangle shapes on there. So if you have that printed out or you want to draw it by hand, draw out that shape and put the labels on there, but make sure that you can explain to someone, anyone, how we get the lengths of the three sides and the lengths of the three angles, the widths of the same angles. Measures would be the better word. I'm going to pause the recording, clear my board, and show you the other special right triangle. This time, for the second special right triangle, I start with an equilateral triangle. Equilateral means that all three sides are the same length, that they are congruent. They can be any length, so we'll call them T. We know that an equilateral triangle has three interior angles that all measure the same thing. They all measure at 60 degrees. This is what we start with. This is not a right triangle. We're going to derive the special right triangle from it. So let me draw it again. And notice my drawings aren't super precise. We don't have to draw everything in trigonometry and math, geometry. We don't have to draw everything to scale. We don't have to be perfect in our drawings. We've known this, well, the Greeks established this because they couldn't draw everything perfectly, and neither can we really. So just try to make it look a lot like it, but don't worry about it being perfect. To come up with our second special right triangle, we drop an altitude, which is a perpendicular to the base that goes through the opposite vertex. And we can see when we do this, we've created a right triangle in here, and we want to extract that right triangle, and then we want to understand what all the properties and relationships are. The first thing that we notice is that when we drew this equilateral triangle, that side length was T, and that was T, and this was T. So when we extract our right triangle, we know that that hypotenuse is length T. What you might know about dropping this altitude on an equilateral triangle is this altitude, being a right angle, does two important things for us. It takes this angle and cuts it exactly in half. So that means that this small angle and that small angle are both 30 degrees, which gives us 30 degrees here. That altitude also splits the length of this side exactly in half. So we know that this side here, this leg, its distance or its length is 1/2 of what T is, which we can also write as T over 2. Both mean the same thing. This angle is the same as this angle, is the same as this angle. Nothing changed when we split and extracted our right triangle. So we know that that's 60 degrees. If you didn't already know that this altitude split this angle, you would easily be able to figure it out because you know that this angle is 60 degrees and these two angles have to be complementary. So 90 degrees minus 60 degrees is 30 degrees. So now we know for sure, we have verification that this altitude split that 60-degree angle. The one piece of information that we're missing is the length of this side. In order to figure out what that is, we have to go to the Pythagorean theorem. I'm going to call that side length B. And we know that we have these two legs, and we have that hypotenuse, and it's a right triangle. So we can write the statement T over 2 squared plus B squared is equal to T squared. The square of the two legs added together is equal to the square of the hypotenuse. Now we just do the algebra. This is T squared over 4 plus B squared is equal to t squared. I'm going to move over to the next column. I'm trying to solve for b squared, so I'm going to subtract t squared over 4 from both sides. I get b squared equals t squared minus t squared over 4. Remembering your fractions, this t squared is 4t squared over 4, and I'm subtracting t squared over 4 from it. That tells us that b squared is 3t squared over 4. And continuing with the algebra, b is equal to the square root of 3t over 2. I'm going to pause the recording, erase my board, and relabel the parts. Here is my second special right triangle. We started with an equilateral triangle. We split it to form a right triangle. That angle translated over to 60 degrees, and the fact that it is complementary with this angle tells us that this angle is 30 degrees. This side, T, was one of the original sides from our equilateral triangle. We saw that splitting the equilateral triangle made this side T over 2. And then we used the Pythagorean theorem to show that the length of this leg is the square root of 3 over 2 times t. Remember that t can be any length, so sometimes we just reduce the relationships to be a little bit more blunt. If this hypotenuse length is 1, then this leg length is 1/2, and this leg length is the square root of 3 over 2. And we know that this angle is 60 degrees and this angle is 30 degrees. This special triangle is often referred to as the 30, 60, 90 triangle. Again, notice that I didn't say the word degree with each one of these, but I wrote it in the symbol as I wrote down the degrees. So it's a 30, 60, 90 triangle. We derive it from an equilateral triangle, and now we know where all the parts came from. I want to show you one other way that this triangle is written down. In particular, the way that the relationships between the sides is written down. We saw that it could be 1, 1/2, and the square root of 3 over 2. People don't always like fractions, so quite often they will play with the idea and get rid of those fractions. So quite often you will see it being written as 2, 1, and the square root of 3. And that's perfectly acceptable either way. All we did when we moved from this triangle to that triangle is make t equal to 1. All we did when we moved from this triangle to that triangle is just multiply all of the side lengths by 2. And that's perfectly fine. One thing I want to point out, because people really have a hard time with this, including me, I have to catch myself on it a lot because we move quickly quite often when we're doing our work, and we need to make sure that we stop and think. Remember earlier when I said in the lecture that the smallest side is opposite the smallest angle. The longest side is opposite the biggest angle. And that means that the middle length side is opposite the middle length angle. When we look at our 30, 60, 90 triangle and we see 1, 2, and the square root of 3, we often look at the 3 and don't think square root. We see the 3 and we react to it quickly. And we quickly judge that the square root of 3 is bigger than the 2. This is false. The square root of 3 is about 1.7, which is less than 2. The hypotenuse is always the longest side on a right triangle. 2 is bigger than the square root of 3. The square root of 3 is bigger than 1. So you have to remember that the shortest side is opposite 30 degrees. The square root of 3 is opposite of the 60 degrees, and the hypotenuse is 2, which is opposite of the right triangle.